In example 3 and 4, we're going to apply L'Hopital's rule to be able to apply these limits, to evaluate these limits. So in this case here, when we take a look at this is not limits at infinity, so we can't use endpoint behavior. So this is local behavior. So what we're going to do first is we're going to test this limit. So we're going to plug -2 into this expression, and we're going to end up with 16 minus 16 over -2 cubed is -8 plus 8. That's going to give us 0 over 0. Okay, well that can be a bit of a problem, but when it comes to L'Hopital's rule, this is a good thing because we now have the condition to be able to apply L'Hopital's rule. And so what we're going to do then is we're just going to differentiate this. So applying L'Hopital's, we differentiate. So I'm going to have the limit as x equals -2. So I'm going to differentiate. So apply L'Hopital's. And I'm going to end up with 4x cubed over 3x squared. Okay, so that's going to simplify to 4 over 3x. So this becomes the limit as x approaches -2 of 4 over 3. The x's cancel, so I end up with x. Well, I can evaluate this limit. When I plug it in, I end up with -8 over 3. So this is my limit. In this next example, we have the limit as x goes to 1 from the positive side of cosecant x log x. So I'm going to plug this in, but before I do this, I'm just going to rewrite the cosecant as 1 over sine because it might be easier to evaluate that as a 1 over sine function rather than a cosecant. So as I plug 0 in, I'm going to approach, sine becomes 0 from the positive side. So it's basically dividing by 0 from the positive side. So 1 over sine becomes positive infinity. Okay, so the denominator comes 0. It becomes 1 over 0 from the positive side. So that's positive infinity. Log x, as we approach the y-axis, it's going down the vertical asymptote. So it becomes negative infinity. And so I have our condition that I can use L'Hopital. So that's what I'm going to do. I'm going to apply L'Hopital's. So applying L'Hopital's, I end up with the limit as x approaches 0 from the positive side. I'm going to differentiate the cosecant and log. So the cosecant differentiates into negative cosecant x, cotan x, and then the denominator becomes 1 over x. And to evaluate this, I'm going to just put the 1 over x in the numerator and the cosecant and cotan in the denominator as sine and cos. I have reciprocal expression on the top and reciprocal on the bottom. So I'm just going to make this into negative x on top so that that x ends up in the numerator. The sine and tan in the denominator of the numerator is just going to go down as sine x tan x. And when I evaluate this by plugging in 0, I get 0 over 0 again. So although this is still an indeterminate form, it does give me the condition to apply L'Hopital's one more time. So that's what I'm going to do here. So I'm going to apply L'Hopital's one more time. And so I end up with the limit as x approaches 0 from the positive side. The derivative of the numerator is 1. In the denominator, I get cos tan x plus sine x secant squared x. And evaluating this becomes -1 over cosine of 0 is 1, tan of 0 is 0, so I end up with 0 plus the sine of 0 is 1. Sorry, the sine of 0 is 0 and secant is 1, so it becomes 0 times 1. So in this case, I'm approaching the, the zero in both cases from the positive side. And that means I'm dividing negative 1 by positive 0. So that's going to become negative 1 times infinity. So this becomes negative infinity is my limit. So that's going to be negative infinity. So we can always check our limits by graphing them. So the first one, x to the power 4 minus 16 over x cubed plus 8. As it goes to negative 2, we can see that it's approaching that value here. So if I just kind of trace along here, you can see that as I approach 0, it becomes undefined. It's hard to get to, there it is. But you can see it's as approaches negative 2, we're approaching negative 2.66, repeating, which is negative 8 over 3. If we switch over to the log one, we can see that as we approach 0 from the negative side, yeah, that graph is going to be heading down the asymptote along the vertical asymptote at 0, so it's heading towards negative infinity, which confirms our limit.